Hello, good afternoon, if that's where you are in the world. I am Mark Elliott. I am the Chief Operating Officer of Europa Science, which is the publisher of Electro-Optics. Today, we're going to be discussing the final six of the shortlisted entries to the inaugural Photonics Frontiers Award, which is there to celebrate some of the most innovative and groundbreaking real-world applications of photonics technology. For those of you who have been keeping an eye on everything, you will know that this is the third of the three webcasts that we are running, where we are presenting the 18 shortlisted entries. Uh, but if you haven't seen them already, or if you're just interested in sharing the information with colleagues, head over to electrooptics.com after this webcast, of course, to read the coverage for more insights and indeed find the details that you need to follow up on what we have been sharing already. I would like to just quickly take a moment to thank our judges. I am just going to give them a quick nod, as is customary at this point. So this is who we are. These are our great judges. They've done a brilliant job for us. They've taken a lot of time to look at the entries that have come in. We had a really, really good response, and they have picked the 18 shortlisted people that we have been giving, or at least 18 shortlisted projects, I should say, that we have been giving some airtime to, and will be featuring online and in print in our special edition, which is out imminently. So thank you very much for their time and expertise in judging these great entries. We have a really, really good panel today. We have six people representing six great projects. They are in the areas of environmental monitoring and sustainability, photonics and optical sensors, and spectroscopy. And there's a real mix of applications and technologies here with some really interesting ideas already in play. So what we're going to do is we're going to tackle them in alphabetical order, and we're going to do that first by the category of environmental monitoring and sustainability. A tiny bit of housekeeping, if I may. There is always the opportunity to contribute a question. So if something is being presented and it kind of fires up a question that you want answered, you can add that information into the little chat screen, which you'll see, I think it's bottom right for you. And we will come to those if we can. I'm going to try and ask some questions as we go as well. And essentially, this is really designed to be a really, hopefully, useful showcase for some really interesting technology. So without further ado, I am going to go on to our first presenter, and I'm pleased to introduce Karim Ruvalcaba, who is going to talk us through a project that we've all got a vested interest in, which is food. And that's about critically how to minimize loss and improve yield. So handing over to you, welcome to everybody that's watching. Over to you, Karim. Talk us through what your project is.
Hello, can you hear me?
Yes, we can
Hello?
hear you, Karim. Yep.
Okay. Sorry. I have a little bit of delay. So I'm sharing my screen. So thank you everyone for having me today. As Mike already have shared briefly, I'm gonna talk to you a small presentation about what was mainly the talk of my PhD, the main project, which was a cooperation between Friedrich University Jena, AMS Osram, and Fraunhofer IOF Institute of Photonics. So let's get started with the motivation, what it was really interesting into my project. So let's talk about the main relevance, the main motivation for me to do in this project. So we have currently 1/3 to 1/4 of the food that has been produced globally ended up either being lost or waste. This represents 1.05 billion of tons in terms of volume, and this represents $1 trillion US in terms of monetary losses annually. So there are many factors that contribute to this global food loss, but primarily we can detect these with the ideal harvesting time. And this happening is a really huge problem because when we harvest, it happens once in a year, and it's for every fruit that we have on the crop. That means that whether the fruit is already ripe or not, whether it is overripe or underripe, it's going to be harvested at the same time. So we need to mitigate this problematic. So in order to mitigate this, I came to the solution doing a photodiode array using two detectors in order to determine the fruit maturity. I see two main applications in different industries. The first application into the industry is with the so-called precision agriculture. We can see here farming drones and farming robots that are scanning every single fruit and is determining whether these fruits already ripe or not. This is a pretty futuristic image, but the immediate application will be into the smart sprayers, where we can see here on a sprayer we will have a ton of these photodiodes, a lot of these sensors that are going to start scanning the plants that we have on the field, and it's going to determine what is the required amount of water that every single of these plants will need. Another application will be to the one machine, a harvester that is scanning the fruits that are in the tree, and it's going to be calling the ones already ripe. So what another application that is going to go immediately to the consumer side is going to be a supermarket scanner, where we can actually just take the fruit, go directly into the supermarket, and we'll know what is the ripeness degree of this fruit. But if we have already these kind of applications right now, it's not crazy to think that we can have an implementation into our cell phone, into a mobile fruit scanner. So this is the motivation and the relevance of this project. Now let's go into the data, what I have done previously, since the year 2023, where I take an 18-week long experiment. And here already you can see on the left side, what is the transition from an apple that going from the flower onto what we know as an apple, reddish. What we can see already here with only an RGB photo, the transition on the pigments between the week 12 and the week 13, flowing from greenish to yellowish. And little by little, we can see how this pigmentation is actually turning into red. This is what we can see with just with a photo. Now let's see what we can see with the spectrum. In terms with the spectrum, we see here a really broad band that goes from the visible, starting with the 400 nanometers, and up to the wire, right into the 2300 nanometers. And for here, you have 12 spectral bands that are really relevant, starting with the carotenoids at 480 and tyrosinas at 550, two spectral bands for the chlorophyll at 770 and 700, and normalization band that is really important in this project, because it was the normalization band, because here you will have the structurally intact internal plant tissue. It's related to actually how healthy is the plant. In order to do this, you have an homogeneous scattering. And here you can also, in terms of the NIR wire, 5 spectral bands in the OH overtones and 3 spectral bands for the CH overtones. Here looks a little bit messy, but now that it's been defined, and thanks to this normalization, you can see how the chlorophyll, it started getting to be decremental onto the week 12, when here we have seen here transition from the pigments, and now the relevant is going to be more into the 480 and 550 up to the week 18, which is the end of experiment where the fruit's already ripe. When we go to the NIR and S-wire, we see that the farther that we go into the S-wire, we see that it's more sensitive, the measurements. So we see here on spot on the week 12, when we look into this window between the 1450 and the 7070, we see a major spot that goes here onto the week 12. And suddenly we found here the spot where everything is stabilized, kind of a thing. But this is going into this region from the S-wire. But if we go into the edge, onto the close to the edge, onto these measurements, we see that here actually you see an arm that is going downwards. But all of a sudden you see a transition. Instead of going downwards, you have an upwards transition. So it was a phenomenon that we have, especially in this one on the 2180 nanometers. And this is in terms of spectrum. You can actually group these in only 5 molecular groups. You can see here the transition on the carotenoids, that is, you have an exponential growth since the week 2 until the week 18. Then you see the same transition from anthocyanins starting from the week 6 until the week 18. And the chlorophylls, that since the week 1, you have a exponential decay. And if you look then afterwards to the CH and OH overtones, here I just pointed out one band from the close to the NIR, so you can see that the farther you go, the more contrast you will have in your measurement. But now you see here this spot that I just mentioned, that you have a maximum on the week 12. This is going to be translated to the fruit development diagram, where you have the stark accumulation, and then you see here a transition actually on the week 12, when you have no more stark accumulation but a stark decline. And this we can actually perceive it. We can perceive this now thanks to the normalization technique and thanks to the S-wire and the spectral bands that we here seen. This is in terms of a spectrometer measurements, but if we talk about a sensor, obviously we would like to have this really small package and small design. So for this, I have used 2 detectors, one based on silicon and the second one based on a 3-5 compound material. And this is primarily the configuration that you will need forward your sensor, where if you want to do a production assessment, you will need to focus on these spectral bands that are going more close into the S-wire. But if you want to do an application in the post-harvesting assessment, then you will need to look into the NIR bands. And so the most relevant key feature about this application, about this project, is the small size and the low cost that will provide it as well. Since you can see already here, the sensor itself, it's smaller than €2 coin. And if you integrate with the light sources, well, it's gonna be a little bit bigger than the €2. But in terms of, if you compare it in terms of size and in terms of cost to an spectrometer solution or a hyperspectral band, a hyperspectral camera, it's gonna the prices are gonna be way lower than a typical application that you will find on the market. So that's pretty much everything for my presentation. And Ray, I'm open to your questions.
Thank you. That was interesting. I mean, the obvious question is, have you shared this with the people doing the work on the ground? Have you been able to take this into a kind of a food manufacturing environment or an agricultural environment to get some sort of feedback on the proposition?
Until now, we work closely to the farmers. We have the direct supplier where these people provide us different types of cultivars of apples. So we test this experiment and was designed based on different cultivars of apples and also with avocados. If you also are interested, this is another slide that I have just prepared that you can also have the same behavior, the same test on avocados on the field. This is primarily the two fruits that we have tested, but directly from the field. But I have also made tests from supermarket tomatoes and pineapples, for instance.
I was going to say, I was wondering why apples actually, and then avocados is quite logical. I'm sure we've all had rotten avocados that seem fine,
Yeah.
when you pick them up in the supermarket and things. So no, it's really innovative. And when you were developing the project idea, presumably that cost dynamic of that very low cost unit cost that you've kind of identified was pretty critical to the scaling. Did that
Yeah.
kind of was that a kind of absolutely central proposition right at the beginning, or did you work that out as you were kind of understanding the technology potential?
No, since the beginning, it was the main target. Since with AMS, the main target is photodiode sensor, really simple solution to bring it into the market. So
Yeah.
since the beginning was the idea to bring a low-cost solution that we know that, okay, with a hyperspectral camera, with a spectrometer, you will have the major resolution, but you want to make this for consumer and you want to expand the manufacturing costs.
Yes, yeah. It seems to me that, as a sort of non-scientist in the room, if you like, this kind of constant push and pull between customization and kind of scalability seems to be the absolutely kind of critical back and forth that you see around all kind of product and project development, from my side. Thank you. I'm really conscious of time. We've got quite a lot of great presentations to go through. By all means, anybody watching, drop a note in the chat, but also critically, contact details are on all these decks. So get in touch with these great presenters because these projects are truly innovative and worth your attention and follow up. Okay, next we're going to come to the topic or the category area, I should say, of photonics and optical sensors. We have a short list of 3 here, and I would first like to welcome Bill Choi from Nanolamba. Bill, over to you, please.
Okay, thank you very much. I'd like to share my screen.
Yep, that's starting okay.
Please, then.
Great. That's it. And then maybe from current slide. That's it. Oh yeah, from the beginning. Perfect. Thank you.
Yeah, thank you very much, everyone. And thank you, Abdel. It's a good introduction into the spectroscopy. Yeah, spectroscopy is widely used in many science fields and industries like agriculture, but including even the space science. The James Webb Space Telescope equipped with a very advanced and expensive spectrometer instrument measuring the materials from the deep space and detecting the materials by analyzing the spectral fingerprint of atoms and molecules and so on. But all those instruments are technology, method is only used by the scientists in the lab, and because the spectrometer itself is too big and too expensive. So NanoLambda came up with the idea and were working on developing the ultra compact, low cost spectrometer technology and device product, revolutionizing the spectrometer technology from analog to digital. So so far the technology is based on the grating or prism, but now we don't use grating or prism at all, and utilizing new nanophotonics and digital computation and advanced semiconductor vapor process, making the spectrometer on a chip. The size and cost will be less than 0.1% of a conventional solution. It's so small, so it can be integrated into any IoT mobile wearable devices to measure the people's health, including blood pressure and blood glucose levels and so on, and also water quality and air qualities. And also, as well mentioned, the food agriculture applications, measuring the food quality, also the harvest time measurement and so on. So, and the last one is light and color measurement. And total addressable market for this one will be more than 5 billion units per year, which is similar to the 6 billion units the camera module shipped in 2024. And compared to very low-cost discrete solutions currently used in wearable devices like the ring, smart ring, and smart watches, they use 2 to 7 different wavelengths, but it's a narrow band and missing some information, and also it's a scanning and also missing misaligned timing for the measurement. But using this spectral sensor, which covers a broadband all at the same time, which provides more information and noise robust. So the measurement data will be clinically accurate multifunctions. So which enables transforming the healthcare industry from the hospital-centered to people-centered, which means enabling the people to measure their health continuously and help them not going go to the doctor's office or the hospitals, and which will save $1 trillion and also saving millions the cost. After more than 15 years, the tenacious effort, we successfully developed the technology and proved the technology working, and launched engineering samples, and currently more than 500 sample customers purchased development kit and samples for various applications in various industries, and including the big IT companies and the chemistries, and also research academias. And we also awarded a few awards, especially the SPIE Prism Award in 2021 in smart sensing category. And as a still startup, we are raising Series A for mass production scale up. So if anyone interested in collaboration or investment, please let us know anytime. Thank you very much.
Thank you. One of the things that always, kind of makes me kind of pause is where you kind of see a project like this, which is kind of moving into many, many different markets. How have you looked, I'm thinking particularly about the healthcare market, which, as we know, is incredibly constrained by regulatory framework and kind of typically quite a slow gestation from, kind of, actual kind of exploration to application. How have you gone through the opportunities and decided which areas to focus on first in terms of application area?
Right. Thank you very much. That's a good question, and that's one of the top priority we've been always thinking. And currently, our focus is this light and color measurement, which is well standardized and easy target, but also it's a more than 3 billion market worldwide. So that's a good target market, and we have over 200, 300 research and industrial customers using our first application device as well. But as you mentioned, yeah, healthcare will be the ultimate target because it will have biggest impact, and yes, it's a very tough market. So collaboration is our core strategy, and we investigating the possibility of, for example, blood glucose, even from the 2009. But we haven't started any real project yet, because it's a better wait and see how mature our technology and how close our technology to achieve that goal. But at the same time, can we get real collaboration partner who has expertise in those healthcare regime and for clinical trials and actual marketing and so on. So now we have some lab prototype tested for ourselves for like pulse, SpO2, and blood pressure itself. But some of our customers already tried to measure blood glucose using our sensor. Of course, it's a confidential, but sooner or later, yeah, we can team up with such customers to develop actual healthcare application.
Wow, interesting. Well, one to watch for sure, because it's a fascinating kind of spectrum I find of companies about how they kind of focus in on the opportunity they're going to kind of target. Thank you, Bill. That was great. I really appreciate that. As ever, follow up with him directly. Anything you want to collaborate with, you've heard him ask, so try and follow that up. Okay, next up, we have Mike Noonan from Swave Photonics. Mike, if it's okay, handing over to you.
Terrific. And Mark, thank you so much. Let me put my screen into presentation mode. There you go. And delighted to share with you what Swave Photonics is doing, and really making for the first time holographic displays a reality. Holography was invented in 1947, but up until now has only existed as a photographic process or through the use of CGI in the movies. And Swave is introducing very soon a chipset. We call it holographic extended reality chipset. Consists of an SLM and a companion compute chip. And it's based upon two breakthroughs. The first of which was pioneered at IMEC, the research institute in Belgium. And IMEC came up with a nanopixel technology with a pixel pitch, half the wavelength of light. And the microphotograph there shows one of our arrays with the pixels, spaced, 300 nanometers apart. And we do this by using phase change material as a photonic element on top of bulk CMOS. And so we get a photonics breakthrough, but with CMOS economics. The other breakthrough is the generation in real time of holographic images. Historically, this has taken either a GPU or quite a bit of compute resources. But we figured out through a technique we call dynamic depth to be able to move an image anywhere in multiple planes of projection, and so low power we can actually embed it into a pair of AR glasses. The other byproduct of this is, because this is a computationally generated image, we can be by definition compatible with prescription lenses, something unique in the industry and really a requirement. And just to reinforce the importance of why the need for such a tiny pixel and how this is so different from other and existing display technologies, we show one of our HXR nanopixels, and again using phase change material as a photonic element compared to LCOS and DLP, more than 450 times smaller than DLP and 170 times smaller than LCOS. But the key and really crucial point is, if you want to steer light, and what we're doing is we're steering light to to create a diffraction pattern, you need to be smaller than the wavelength of what you're steering. And here we show the comparison of our pixel to blue light. And again, this requires us to be less than 300 nanometers spaced apart. Existing state of the art for other technologies is order of magnitude too large, and we'll never be able to do holography in an effective manner. And what this means is, for the first time, we're going to be able to really deliver on the promise of AR and really the emergence of AI when it comes to personal devices. And then, in fact, our first market is going to be AR smart glasses that are fashionable, lightweight, comfortable, truly usable, with all of the features that everyone would want, but up to now have been unattainable. Lightweight, all-day battery life, solving vergence accommodation, which is the phenomena that basically the human vision system after millions of years of evolution expects things to behave in a certain way. We solve that with daylight brightness, huge field of view, and again this crucial prescription glass compatibility, but at the same time dramatically lowering the cost of goods sold. Again, leveraging the fact that you were using bulk CMOS as basically our platform. And worth noting, this technology, because of its huge field of view, does not need a pupil replicating waveguide, which eliminates a significant cost and source of inefficiency. The device in the first prototype of our spatial light modulator that we call Onyx has 256 million of our nanopixels, a quarter gigapixel on a 7 by 7 millimeter die. And we'll be sampling these to our early customers later this quarter. And just to put it in perspective, on this die, smaller than a fingernail, we have more pixels than the Sphere in Las Vegas. So it's been a delight to share with you what we're doing at Sway Photonics and bringing holographic technology, not only to AR smart glasses, but to many other formats that this new age of AR and AI compute will bring about.
Wow, it's a really good example, isn't it, of kind of how technologies are colliding into kind of new application mixes. It's it's a very powerful comparison. I love that context of versus the sphere. I had a question around the glasses. Inevitably, I'm sure everybody kind of fixates on those. Those technology breakthroughs that you listed, battery life, weight, all that sort of stuff. What do you think from the research you were doing was the most important thing to fix with this? What was the most critical of those breakthroughs on that list?
Well, that'd be a great question. And really, to make holography our reality, we really needed to reinvent the pixel and get a pixel that was smaller than the wavelength of light, because to do true beam steering, you need to be in this new physics regime. And I give a lot of credit to IMEC, which uses the entire periodic table of elements to innovate with, to do something kind of out of the box and use phase change materials as a photonic element. And Swave, is really benefiting from that technological breakthrough, and now productizing and really also the siliconization of photonics is what we're putting in play here, and so that reinvention of pixels has allowed us now to enjoy all these benefits. But it took this kind of Herculean step forward to have this half lambda pixel.
Yeah, and sorry, another quick supplementary, if I may. Patents with this, have you been able to patent this? Yeah. Okay.
Indeed, and it's another benefit of engaging with IMEC, which has a very rigorous patent program.
Yeah.
So we actually have 14 patent families that cover all the way from the semiconductor physics all the way through the applications layer. And so pioneering this brand new area as a result has brought with it a very large and defensible patent family.
Wow. Okay. Great presentation. Thank you so much. That's really interesting.
Thank you so much.
Okay. Next up, and apologies, we're rattling through this. There's a lot of great stuff to get through, and we are trying to keep this within the hour. So next up, we have Mario coming from Anello Photonics. Welcome, Mario. Over to you, if you may. Thank you.
Thank you. Can you hear me?
Yes, we can. Yeah.
Okay, let me put this in. So first, thanks for the opportunity. It's a pleasure to be here, and it's interesting to listen to these other speakers. So what I'm going to talk about, I'm the CEO and co-founder of a company called Anello Photonics. Anello in Italian means ring, and hopefully at the end you'll understand where that came. But we're the creator of what we call the SiFog. It's not SIPHOG. It's SiFog, silicon photonics optical gyro, and I'll explain what that is. So at a high level, what we tried to do is, if you look at gyros today, gyros measure rotation. And there's two types of gyros. There's what the common gyro that's in your phone today. That's on the y-axis here is bias, degrees per hour. Above this half degree per hour, it's all MEMS based. This is what's in your phone, what's in your AirPod, in your watches, and it measures course position, gaming. Billions of units per year, high volume, low cost. The problem is it's not very accurate. You know, MEMS is a floating membrane, it's a capacitor, so it's very susceptible to temperature, vibration, electromagnetic interference. And so it's not very good for accuracy or navigation. If you go below this line, half degree per hour, it's predominantly based on fiber gyros. And these are big, bulky. This is a 3D print of a fiber gyro. You'll see that in a minute. They work great. That's what's in all ICBMs, fighter jets, submarines, way down at the bottom. The drawback is they're big, they're bulky, and they're expensive. And expensive means $30,000, $40,000, $50,000 on the low end, hundreds of thousands. And so when we looked at the navigation market, and you look at this new autonomy, which I call the mass market of autonomous cars, autonomous trucking, drones, agriculture, the concept was, hey, what if we could build a gyro that's small, lightweight, low power, can produce in high volume, but still has the performance of a fiber gyro. And you'll see this line at about a half degree per hour. There was this gap. Physically, the MEMS can't get there. Fiber gyros can get there, but you're not going to take a gold-plated box and shave the gold off to make it cheap. So we had this concept of what if we created this SiFog? And you just heard the talk earlier, but based on using integrated silicon photonics, which is basically taking photonic devices and putting them on the standard silicon processing that's being used today in the electronics industry, and create a fiber gyro on a chip. And this is what we call SiFog. And we would target this middle gap. And if I can do this and get that type of performance, I can get both the industrial market and with predominantly the defense market, and open up this entire new market opportunity to bring high precision, high capability sensors to this new growing autonomy market. And so the picture on the left is a cartoon of how a fiber gyro works. At a high level, it's very simple. You have light going into a crystal. It goes into a coil in two different directions. As that coil rotates, the light going in the same direction as the coil goes a shorter distance than the other. You merge those two beams and you get an interference pattern. And if you can measure that interference, you can measure the rotation rate. The picture on the right is our lab setup. It's about $65,000 of stuff: lasers, amplifiers, detectors, phase modulators, lithium niobate crystals. That little thing on the table, if you zoom in, this is the SiFog. So we put everything on that table into this small device that fits in the palm of your hand. How do we do that? Based on integrated silicon photonics. So the picture on the middle, this is the actual chip. It sits in the fingernail. It's literally 2 millimeters by 5 millimeters. And in that device, we have all the splitters, the couplers, the phase modulators. There's about 34 components on that chip. All these devices had to be created. The models had to be created. And we started the company, unfortunately, right when COVID hit here in the US. And so there was a long process. But the second thing is we have a planar device based on silicon nitride, or we use a fiber spool to create a very tiny loop. You put those together with a bunch of electronics. This is a zoom in of that chip, the electronics and the whole board. And what you end up with is a smallest optical gyro in the world. It fits in the palm of your hand, low power, 3.3 volts, no moving parts, not susceptible to vibration, not susceptible to temperature. More importantly, assembled just like the semiconductor industry, high volume, pick and place, and now we can scale this to the mass market. So that's the first piece, SiFog. The next thing is, what can we do with it? So now we take this SiFog and we put it in the systems. If I put it into a box with CPUs, sensors, sensor fusion, algorithm, GPS, I can create solutions. And these are products that are shipping today. This is for land vehicles. This is a unit. This is for robots without the GPS. The cool thing is if I put 3 of those into a cube, now I have the world's smallest IMU. This is for things that move in 3 dimensions, things that fly, drones, maritime. If I look at just the size difference, this is the state of the art today. This is our new X3, which we call it for aerial maritime. Let me show you how this works. This is agriculture example. In the fall, the leaves come in and you basically go up and down these orchards. They want to automate this for spraying. It's nasty. You don't want people there to do it at nighttime. You need to have this tractor automatically go through. It's a very simple problem, half a mile long, 3 to 5 miles per hour. The picture on the right is our solution. The picture on the left is a competitive solution. And you can see we can navigate directly through this just because we're putting this high precision gyro, which measures heading, into an autonomous system. So there's two things. There's jamming. And in the industrial world, jamming is you lose the signal. Tunnels, bridges, downtown urban canyons. In the defense world, jamming is real jamming and spoofing that's happened, unfortunately, in war-torn areas. Let me give you an example of spoofing now. Spoofing is when you get the signal, GPS, but how do you know if it's good or bad? Because we have this accurate gyro now in a system, this is an example. We literally can put this on the dashboard with this kind of accuracy. What you're seeing here is spoofing that's happening with a DoD event. The background's been wiped away, so you can't see where the testing was done. But the green is the vehicle driving, and orange is GPS. So now we have the ability to, every 10 milliseconds, we compare our position real time. These systems have accelerometers, gyros, temperature sensors, magnetometers in them. It gets fused together. We measure our position real time with GPS. And if you're driving in 10 milliseconds, all of a sudden GPS says you went to Texas, like the picture on the left. Hey, something's wrong. You're being spoofed. Pour over 100% to Anello. The middle one gives you a better example where the spoofing is very subtle. And now we detect this. We have algorithms to look at about 14 or 15 things. We can tell if we're being jammed. We can tell if we're being spoofed. And we use our system to develop and use Anello when GPS is bad or when GPS is not working well. We have systems that we're shipping into agriculture. We have systems on drones. Drones is very similar. Drones fly 100% on GPS. If they lose GPS, what happens? They don't know what to do. They sit there, they hover, they can't return to home, they crash. We modify the software. We say, don't worry, port over to Anello. And lastly, maritime. You're bopping around in the water, all this autonomous boats, USVs. You can use LiDAR, you can use cameras, but everything looks the same. We now have a system and solution that's 100% dependent on nothing else but the gyro. And this is today, we've created this new SciFog. We have systems, land, air, and sea. And if we look where we're going forward, we've created this new sensor. We'll continue to integrate, we'll continue to shrink just like the electronics industry. We are in the top markets today, agriculture, construction, maritime, farming. Over time, we'll start going into industrial robots, gaming, and eventually we're going to make this chip small enough that everything will be included, laser, detector, gyro, and this eventually will be in everyone's phone, everyone's wearable device in the future. Thank you.
Wow, great. Really interesting. I loved your kind of definition of big, bulky, and expensive. Never words anybody wants to hear in terms of product or technology development, really. So it sounds like you've kind of nailed a kind of a solution to that pretty tightly. Can I just ask, I mean, obviously some of those contexts, some of those kind of environments, these will, are quite challenging. And you mentioned things like heat, vibration, etc. Has there been any of those contexts which have been more challenging? Is there any kind of slightly weaker than the rest spot? And apologies for trying to pick holes in
No. I think you're right. So a lot of these, like I'll take that construction, farming, agriculture. These are harsh environments, right? Yeah. It's dirt, dust, bumpy, salt spray in the maritime. So all these systems, while they look, this is not about heat, they're very low power, they're ruggedized. So this is an auto-grade connector, salt spray, you can throw this in a pool. So we've taken into account hardening these systems for those environments. And that's across all the product lines. And the other benefit is because it's photons and it's just light, they're not dependent on any of this stuff. So vibrations don't affect photons, right? The shock and vibe from an optical solution don't affect photons. And so we've designed these systems, and granted, it's been trial by putting them out in the field. We've gotten feedback. The first couple of units, obviously, when we tried them, weren't sealed properly, and so we've taken almost to the extreme now. We have a solution that can stand those harsh environments, and that's how we're able to do land, air, and sea.
Yep.
The only thing we haven't done, and I'll to your part, Mark, we haven't dealt with hard radioning in space yet. So the next frontier, maybe the last frontier, depending on who you ask, there's a lot of interest in using this technology in space, and we haven't done space testing for radiation, and that's coming in the future.
Okay. Have you got anybody lined up to work with on that? So, is that
we have a bunch of people interested, and so anybody's in the space we're happy to. Right now, it's just not the priority to do the testing. There's lots of interest. There's a couple of companies here in the U.S. that are launching reusable rockets that are very interested in putting this up in space. And so, you have to pick and choose where you focus in the beginning. And I have a board that's trying to keep me focused on shipping what you have versus what you don't have, right?
Yeah, keep focused on the immediate goals.
But the key is we've developed this new sensor, which is a core that now allows us to bring this world from big, bulky, expensive, high end to the mass market. That's the revolution.
And your board should be happy because there's a lot of easy wins and some medium-term, longer-term stuff as well.
Yes, well,
the perfect model
for all of us who knows. Sometimes we got some. There's always one or two board members that it's never enough, right?
No. That's their role, right? Okay.
Right.
Thank you.
Thank you, everybody.
That was terrific. Okay, so some really strong projects there. Thank you to all three in that category. And now the final category, by no means last, but certainly not least, but coming up last in terms of keeping to the alphabetical regime that we fixed on. So we got the spectroscopy category. We've got two entries that were shortlisted by our judges. And first I want to present here's Slava from Art Photonics. Over to you, Slava.
Yeah, thank you. Sorry.
That's great.
Okay.
Yep, that's coming through fine.
Is it on the screen now?
Coming through. Yep, you're good to go. Thank you.
Okay, great. So I'm a bit different from all the previous speakers because I was focused through the whole life into the components, and this is fiber optics. So not a complete system, but fiber optics. And I should consider my way from science to business by, how to say, lucky steps that I was lucky to get my alma mater with good competitions. And I was head of laboratory of applied fiber optics in institute. And then due to some kind of terrible time for Soviet Union, for Russia in 90s, I spin off my laboratory into the joint venture like Soviet, German, American venture Ceramoptech Systems, and it was kind of good business school for me. And then I learned how to make management of the projects in Europe. And the photo at the left, you see historic photo when I sit with my kind of guru. It's a Nobel Prize for laser invention, Professor Alexander Prokhorov. He suggested me to change the world of fiber optics, not to limit it by, let's say, UV to near-infrared range, because you know that all silica fibers are limited to 2 microns or 2.2. And to go into mid-infrared fiber optics. And my baby, which I developed through my, how to say, diploma, PhD, what else, it's a kind of a very unusual fiber. We name it polycrystalline infrared fiber, PIR fiber, which is really nanomaterial with a grain size like tens to hundreds nanometers. And unique feature of this material is that it transmits radiation up to 16 microns, so in so-called fingerprint region. So that's why with this kind of unusual baby, we are probably one of the first and more or less unique commercial manufacturer today, starting from this, let's say, joint venture. Then next was, next was, let's say, how to use, what for. The first application was like flexible cables for medical CO2 lasers. You see them at the left, and we developed very special technology how to suppress Fresnel at the fiber end by microstructure. Then Our fiber, because it's transparent in mid-infrared, can be used for infrared endoscopes. So that's why we were lucky to work with great partners in America to develop the very first endoscope. So that's why everybody is familiar with infrared cameras. But camera will give you a chance to see only straight light. With our mid-infrared fiber, you can go inside human body and see temperature spots inside, which is probably, for example, cancer detection, because cancer is a bit warmer than normal tissue. I should say my presentation is mostly like steps, to very first products. We were the first who developed very special single mode fiber for mid-infrared in European Space Agency program Darwin. We did it with Astrium, and we were the first in 2004. Then, in general, another, steps forward were really development of diamond ATIR probes for FTIR spectroscopy, because fiber optic bridges between any spectrometer and target, reactor, pipe, human tissue is really, I believe, it's my dream, will change the world, because today 90% of people, they simply would like to know composition of, let's say, beer or oil, and they put sample into the spectrometer in laboratory. But I name it spectral pathologoanatomy, because what you do with a sample, you put it in garbage after the tests, and you could not do it when the reaction runs at, let's say, high temperature, high pressure, toxic, aggressive, what else. Fiber optic bridges will give a chance to make live spectroscopy inline. You can go in your engine and see in liquid phase what's going on in combustion camera. You can control exhaust composition. And everything will be done with fiber optics, because there are almost no optoelectronics which will survive, let's say, temperatures from, let's say, 5 Kelvin up to 300 degrees C, and we have this kind of products. Then we are not, narrow-minded for mid-infrared fiber optics only. We developed in 2015 a multispectral fiber system using all 4 methods of spectroscopy. You see here, for example, FTIR spectrometer, Raman, near-infrared, and fluorescence. We really use it to help surgeon to make less mistakes. Maybe you don't know, but today surgeon makes from 50 to 70% mistakes, because he does not know exactly where is the tumor border, tumor margin. So that's why with our kind of sensors, fiber optic sensors, you can touch and really know much more precisely where is the tumor, malignant cells, and where is the normal tissue. Our excellent collaboration with company Reverdi in Holland resulted in special Raman probe, which is also multispectral, so it's fluorescence in Raman. And that was, let's say, tiniest fiber optic probe in the world, because it's diameter smaller than mosquito. So mosquito has about 200 micron. We have a single fiber probe which can go in tissue very fast, 1 second, 1 centimeter. Every 100 milliseconds we knew malignant or normal. Okay, latest results were really the very first project when we couple quantum cascade lasers for 5 to 15 microns with our fiber optics. So it's kind of the very first fiber optic coupled QCL systems. And then, the very last results, which I just forgot to put yesterday and put today, we really developed the very first combi probes. So when we unite NIR and Raman method in one fiber probe, ATIR absorption with fluorescence, and ATIR with Raman. So that's why we try, maybe I'm still scientist in my, bottom in my heart, because we always try to make something first, to be kind of icebreaker, But I hope that the dream about this spectroscopy fiber system will be converted in, how to say, Internet of Things, because it will be sensors which will be used inside any reactor, inside human body, and even back to very historic request we got in 90s, from Kronenburg beer in Strasbourg, how to control fermentation process to make good beer. So that's why we are moving in this direction, and I would like to say that now we have already partners, because since last year we joined Nynomic Group, and we have 11 partners who make spectrometers, systems, and so on. So that's why my vision of my rest of the life, I'm only 71. It's a lot of time for me to do something new. I really would like to make complete systems, complete spectral fiber sensors, and I'm looking for partnership.
Okay, so you've heard it there first. Get in touch with Slava. The judges were really impressed by the diamond enhanced ATR fiber probes, for a range of industrial spectroscopy uses. So it's really interesting. I've got some questions, Slava, but I'm going to ask you those separately, because they're a bit too broad for this and things.
I could only say that with Bill, I hope that after this conversation, this telecon, you will send us, let's say, email addresses. I'm really very interested to talk with Bill Choi about, let's say, combination of his spectrometers, synergy with our fiber optics.
Okay, perfect. This is what we like to hear. Collaboration forming out of these things. Right. Apologies to Mike Hardy, who's been waiting silently in the background all the way through. I've got a bit more time. So, over to you, Mike, to talk through your presentation.
Great. Thanks, Mark. Let me see. Can you see my slides?
Yeah, you're good.
From the beginning. There we go. Okay. Oh. There we go. Oh, still doing something funny. Okay. I'll maybe leave the mouse. Let me see. Can I close that? Okay. Can you see my slides? Okay, is that good, Mark?
Yep, that's good.
Yeah,
good.
Thanks. Okay. Hello everyone. Good afternoon. My name is Mike Hardy. I'm a research fellow at Queen's University in Belfast. So big thanks, as I say, to Mark and David and the whole electro-optics team for having us. That's the topic at the bottom. I'll say a little bit about more about that in a minute. Oh, presentation. Sorry, Mark.
No, don't worry.
I'm going to take the mouse out here because I think maybe that's causing problems.
Yeah, do the arrow.
Yeah. Okay, so hello from Queen's. That's where we are. I should say the weather in Belfast is not normally, it's not representative of how it normally is, but it was nice that day, so I took a photo. So hello from us. Oh, no, it's not so good. Sorry, Mark.
It really doesn't like your mouse, does it?
Yeah. I took the mouse out, so.
Do you want me to drive?
Maybe that would be a good idea.
Okay, give me 1 sec. Let me just get this on.
Let me see.
Don't worry.
Sure. What's going on? Maybe I'll give it one more go here because.
Okay.
No, it's not.
Okay, that's fine. Don't worry. I've got it. We're on the slide. There we are. I'm hopefully
Is that
okay
now?
Can you see that?
Yeah.
Okay, right. You're on.
Yeah, it's okay. Maybe. Okay.
Yep.
Okay. Is that okay from there? Maybe.
Yep. Can you see all that? Everyone see all that? Okay.
Yeah. Is that okay?
Yep.
Okay. Okay, there we go. David and I were always saying there's some issue with things. Okay, so a little bit about our project. We're a collaboration between photonics-based companies in Northern Ireland and the two universities, that's Queen's and Ulster, and we work within the themes of photonics, nanotechnology, and smart manufacturing. So that's using data to improve processes. What do we do exactly? I never like that question because we do lots of different things, right from computer-aided design, light simulations in different scales, micro manipulation on of different sorts. We also do a bit of standard physics, lasers, optics, that kind of thing, and of course we do the data work. I don't think anyone can get away from that these days, but it's all good. Okay, so the project I will speak about today, very briefly, is some of our spectroscopy work for the testing of some of the fidelity in some of these nano imprint lithography made sensors. Okay, so we've talked a little bit about Raman scattering. today. Raman scattering, the inelastic scattering of light. So light interacts with molecules when we have a wavelength or an energy shift, and that can tell us what the molecule is and how much of it we have. Unfortunately, it's a very weak effect. So we